infinity over infinity when we were taking limits, right? And this was a problem. And we said anytime we see that, again, we want to do some algebra or some sort of trick. And here sometimes we would look at the highest power in the bottom, multiply the top and bottom. Do you remember that? Okay, so there was that. And then were there any other issues we ran into? Let's see. What about if we had like fixed over infinity? Was that a problem? That was not a problem. Anytime we saw that, that went to what? 0. Okay, so that check, okay? This, it depends on the problem, right? How about if we had this? What about fixed over something going to 0? Was that a problem? This is either infinity or negative infinity or does not exist. So we did have answers for this. So we could handle that, right? These are still the two that we just not quite sure about. The top wants to be 0, the bottom wants to be 0. You can't divide by 0. Problem. This one's getting big, this one's getting big. Who wins, right? Who's getting bigger faster? These two are called indeterminate forms. When you take a limit and you get something like this or like this, you cannot determine what the answer is until you do something. You have to do some algebra or something, trick. But these are not the only two indeterminate forms out there. There are several other indeterminate forms that when we get them in a limit, we still can't tell what's happening. So let me show you what those other indeterminate forms are. And see if you can. So those two, we're good. All right, how about this one? How about we do something like this? 0 to the 0. Now I want to be very clear on something. I am not asking you right now, what is the number 0 raised to the number 0? I'm not asking you that. I'm asking you to consider an expression where, like if you took the limit, right, this expression, if I say, hey, let x go to 0, then wouldn't this expression go to 0 to the 0? Right? So I'm saying in the limit, if you ever get this expression, or in the limit you get this, or in the limit you get this, then we have indeterminate forms. I just don't want you to walk away from this thinking that I'm telling you that 0 to the 0 actually means something. It doesn't. It's in the limit, if you get 0 over 0, do we have a meaning for it? So why would this be a problem? Think about why this is problematic and why we cannot determine what the answer is to this if we're taking a limit. We kind of just talked about it. What's the conflict happening here? 0 to any power should be 0. But we've learned that anything raised to the 0 should be 1. So it's like, who wins, right? Who wins? Does the base win or does the exponent win? Or do they compromise and have some middle ground? Because that does happen. We do sometimes have a compromise. It depends on the expressions. So this is indeterminate. What about this one? Your base wants to become infinitely big, right? So you're taking a limit, the base is getting huge, and your exponent is trying to be 0. Why is that problematic? Because anything to the 0 should be 1, right? So the base is sitting here going, I want to be big, and the exponent's up there like, nuh-uh, I want to turn you into 1, right? That's, again, you have this tug of war happening. Does that make sense? So that's an issue. How about this one? No, let's not do that. Okay, hold on. Is that an issue? Remember, I'm saying in the limit, okay? In the limit. Everything here is prefaced by in the limit, we're getting this. So am I saying the number 1 raised to the infinity right now? I'm not saying the number 1. I'm saying something that is wanting to get really close to 1, right? This base is trying to get close to 1, right? And the exponent is trying to multiply that times itself an infinite number of times. So the base is like sitting there going, look, I really want to be 1, and if I could ever get to 1, 1 to any power should be 1, right? But the exponent's sitting there going, look, you're not 1, right? And I'm going to keep on making you multiply times yourself. And so you might get bigger, right? It is possible to go smaller, but that's only if this number is smaller than 1. But let's not get into too many details right now. I want you to see that there is a conflict there, though. Do y'all see that there's a conflict? Sure? Okay. These are all indeterminate forms so far. How about this one? Is there a conflict here? I'm open to suggestions here. So what does the base want to do? What is the base trying to do? The base is like, I want to be big, right? I want to be a huge number, right? And the exponent is sitting there going, and I want to multiply you times yourself many, 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 many times, right? And so they look at each other and go, well, then we're on the same page, right? I want to be big. You're going to make me bigger. This is going to blow up. We're going to blow up, right? We're going to become infinite, right? Do you have a question?
Well, I guess I was just wondering, would it not be infinite because infinite times infinite is infinite?
That's right. That's what I'm saying. This is not a conflict. This is not an indeterminate form. There is no tug of war. They both want to achieve the same goal. The base wants to be big, and raising a big number to a big number is going to get bigger. So everything is happy. This is not an indeterminate form. Which one? What if the base was negative infinity? That would be a problem because you would have this switching of signs happening. Because, you know, if you take a negative number and you raise it to an even number, you're going to be positive, and then an odd number, you're going to be negative. So, yeah, we won't look at that. But yeah, that would be weird. It would still explode, but it would explode kind of like this pattern where it's going back and forth.
I wonder what the graph would look like.
Of what? Something like that? We'll look at. Oh, it would be like that salt and pepper one. It would be scattered. Yeah, it would look probably like up, down, up, down, up, down, up, down, like that. All right, so the reason I put that one up there is because I don't want you to be sitting there going, anytime I see like any weird thing like that, it's always indeterminate. It's not always indeterminate. How about this one? How about this one? 1 to the 0. Remember, in the limit, you get something where the base wants to be 1 and the exponent wants to be 0. Is that a conflict or not? No conflict. The base is like, I want to be 1. The exponent's like, I make things 1. Right? Like, we're going to work together. This is going to be great. Okay? No issues. Right? So are there any others that I'm leaving out here?
About
0 times infinity? What do y'all think? So am I saying take the number 0 and multiply it times the number infinity? That's not what I'm saying, right? I'm saying we take a limit and we have one expression that wants to go to 0, right? Wants to become very small. And we have another expression next to it that wants to become very big. So who wins? Are they on the same page or not? They're not on the same page, right? I want to be big, you want to be small. What's going to happen? Don't know. It depends on the functions themselves. It depends on what they're doing. How big, how fast is this one getting big and how fast is this one getting small? This we don't know. Indeterminate. Any others? Sorry, what? 0 to the infinity. Good, I'm glad you mentioned that one. 0 to the infinity. This is a good one. Is there a conflict here? You don't think so? Can you rationalize why you don't think that's a problem?
0 wants to be 0, and if you multiply 0 by 0,
Okay, so the argument here is that this base wants to be 0, and this would say, okay, I'm going to keep multiplying 0 times 0 times 0, which would be 0. I agree with that, except for the fact that this is not 0. It's close to 0, right? So, like, what if it's like 0.1, let's say, and I raise that? So, but you're on the right track, because what would 0.1 squared be? Would that be bigger or smaller? 0.1 squared is actually smaller. It's 0.01, right? And then what's 0.01 cubed? Even smaller. 0.01 to the fourth, even smaller. So this one wants to be small. It's not 0 though. And this one's like, look, I'm going to multiply you times yourself over and over and over, right? And this guy's like, well, that's a good thing because I want to be small, and when you keep multiplying a number that's smaller than 1 by itself, it gets smaller. We agree with that? Any number that the absolute value is less than 1, you multiply it by itself, it gets smaller, doesn't get bigger. That's a misconception people have. If x is equal to some number, right? Let's say x is equal to some number. People think always that x squared must be bigger than a squared. I'm sorry, x squared must be bigger than x. That's not always true, right? If I tell you, hey everyone, I've got this number, I'm going to square it. Is it bigger or is it smaller? Most people think when you square a number it gets bigger. That's not always the case, right? If I take the number 1/2 and I say square it, it becomes what? 1/4. That's not bigger than 1/2. Now, if you pick a number that's bigger than 1, like 2, and square it, then yes, I agree with you. So that's what's happening here. This number right here is small, and you keep raising it to bigger powers, it gets smaller. So this is not a problem. Let me make sure I've covered them all. 0, 0. Do y'all have that sheet? Yeah, that's the only one I haven't done. But are there any others with powers? I don't believe there are. On your little cheat sheet, I think I've got them all covered. Yeah, there's one last one. Infinity minus infinity. So if that was infinity plus infinity, there would not be an issue. Because big number, you're adding another big number, it's going to be a big number. But if I tell you I've got this really big number, and I'm subtracting this really big number, you don't know if it's 0. Because I'm not telling you how big this is. I'm not telling you how big that is. Just that they're both big. So that you don't know. So everything you see up here, right, that's not crossed out, is an indeterminate form. And we need to be able to handle them. Okay? We need to be able to handle any of those. The only ones we've ever played with in this class are these, right? And even with these, we have some we don't know how to do. I've just told you how to do them. Yes? And then comes along L'Hopital. All right? L'Hopital is, you're going to love L'Hopital. You're going to love him. You're going to love the formula. You're going to love the man. He's dead, but you're still going to love him. Okay? So L'Hopital's rule. The hospital. I would just go up and give him a big hug if he were still here. Just thank you. Thank you. Okay, L'Hopital's rule. You know what? I've liked L'Hopital so long. I'm going to have to go back and do some research on this. But I believe last year in my Cal 1 class, I did a little research on L'Hopital. And it turns out that L'Hopital was not the person who came up with the rule. That somebody else came up with the rule, and that person was kind of broke, and so this person was helped fund them to do research, but anything they discovered had to go and become that person's, their name goes on. I'm gonna have to double check that. Allow me to double check that, because something tells me it's not L'Hopital. Okay, I'll look into that later. But I still love L'Hopital. I'm still going to love him, okay? All right, so here's the rule, okay? It's such a simple rule. It says this. If you ever in your life are doing a limit, And it does not matter what's approaching what, okay? It could be x is going to 0 or x is going to infinity or blah, 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 who cares? And what you have is on the top you have some function, and on the bottom you have some function. Okay, so if you ever have that limit and that is headed towards 0 over 0, or it's headed to positive or negative infinity over positive or negative infinity. So you're taking some limit, you've got a ratio, the top's headed to 0, bottom's headed to 0, or the top's headed to infinity or negative infinity, bottom's headed to negative infinity or infinity. It doesn't matter if they're positive, both negative, one's positive, doesn't matter. As long as they're both going to infinity. In either one of these cases, okay, if that's true, then that limit that you're trying to find, this is what we're trying to find, right? That is equal to this limit. If it exists. Some limits just don't exist. You just can't, there's just sometimes we just can't take a limit. The limit doesn't exist. But if the limit exists, it's equal to this. Do y'all see what I'm saying? Do y'all see what I'm saying? This L'Hopital's rule is going to allow you to do? Take the derivative of both, right? The top and the bottom, and then go do that limit. So it says, look, let's say you're taking this limit and you're having trouble, right? You run into 0 over 0 or infinity over infinity, and you're like, I don't know, I can't tell. There's no algebra, or something, there's no trick that I can come up with. L'Hopital says, it's okay, don't worry about it, don't worry about it. Take a look at each of their derivatives. No quotient rule here. This is not a quotient rule. He's saying just take derivative of the top, take derivative of the bottom, look at that limit and see if it's any better. Whatever that is also this, all right? And I'm not going to prove this to you. The proof of L'Hopital's rule is beyond the scope of this class. All right? We just get to use it. So let's go back to what I started this with. Oh, sorry, I didn't start with that. I started with this. I said, do you all remember that? And everyone was like, yes. I said, you remember what it is? Yes, it's 1. And then I said, why? And right? So let's act like we don't know it's 1. We take the limit. What do we get when we take the limit? 0 on top, 0 on the bottom. Because of that, 0 over 0, we are allowed to use L'Hopital's rule. So my next line, what I'm going to do is put equals. Now I need to somehow let you know, or let whoever's looking at my work know that I'm about to break out L'Hopital's rule. So there's kind of a standard notation. A lot of books will put on the next line an H on top of the equal sign to let everyone know they're using L'Hopital's rule. For some reason, when I was a student of this and learning it, maybe I just didn't read my solutions, or I don't know, I wasn't paying attention. I have always just done an L and circled it. I don't know why. Do an H, do an L, whatever. Just somehow notate the fact that you're doing something, all right? Other than just saying that this is equal to this. Okay, so L or H, doesn't matter. That's saying L'Hopital. To me, I like the L. So equals, let's see, limit x approaches 0. And now, what is it the limit of? What are we going to take the limit of? The top's derivative, which is cosine x, over bottom's derivative, 1. Okay, now try that limit. As x goes to 0, cosine of 0 is 1 over 1. 1 over 1 is 1. And we're done. Okay? Now you don't, again, don't ask me why, like why does it work, unless you're willing to sit down in my office for a while. And even then, I'm not quite sure it's achievable, like if it's doable. You know what I'm saying? Like mathematics is a language. And there comes a point at which, in order to explain something, I might have to speak to you in a language that you won't understand. Right? So we're just not ready for that. Isn't that awesome? That's great. Do you remember this problem? You all loved this problem. I always remember the things y'all loved. This one you loved. Ah, that's that weird one. Do y'all remember that weird one? This is the one where you had to like peel it apart, and you had to like figure out like, I need to put a 3 in there, and it'd be really nice if I had a 5 there, and then I could slide the x over. Do you remember all that? Yeah. Okay. Okay, let's just do the limit real quick. What do we get on top? Sine of 0, 0. So we get 0 on top. So this is headed to 0 on top, and it's headed to 0 on the bottom. Okay, so that qualifies for L'Hopital's rule. As long as we can take derivatives, we're in business. All right, so I'm going to say L'Hopital. L'Hopital. I think in my solution videos, I like seeing L'Hopital like the whole time I'm doing them. I apologize ahead of time. Okay, now be careful. What is the derivative of the top? Cosine of 5x times 5. Now we have to still take our derivatives properly, right? That's chain rule. And then over, now the derivative of the bottom. Secant squared of 3x times 3, because chain rule again. And now try and plug 0 in. Okay, what's cosine of 5 times 0 is still 0, so cosine of 0 is 1. 1 times 5 is 5, so the top's headed to 5. And I just better hope the bottom's not going to 0. Okay, secant of 0. Remember, secant's the reciprocal of cosine, right? So what's cosine of 0? 1. The reciprocal of 1 is 1. Just flipped. So just 1 still? Here, maybe I should look. This is secant. Secant squared of 3x really means 1 over cosine of 3x, that quantity squared. That's what secant squared means. So if I go x to 0, I get cosine of 0, which is 1. 1 over 1 is 1. Squared, that's still 1, right? Times 3. Done. No magic sliding things over and making things appear and disappear. God. So much faster. How about this one? How about this one? How about this one? Limit x approaches infinity this time. X squared minus 3x plus 1 over 2x squared plus x. Yeah, minus 4. Okay. So I can remember a few weeks ago, I was standing right here, and I was going through a problem like this. I can remember it vividly. And we were saying, okay, what happens as x goes to infinity? Infinity squared is going to be infinity. And then we said minus 3 times infinity. But this one would overwhelm this one because this one's squared and this one's not. And then we said plus 1 wouldn't matter. So basically we get infinity over infinity. And what was the technique for this? Look at the highest power down here. Multiply top and bottom by 1 over x squared. And do all that stuff, right? However, this is really headed towards infinity over infinity, isn't it? Yeah? Okay, if that's headed to infinity over infinity, then I can use L'Hopital's rule. Limit x goes to infinity of derivative of the top. 2x minus 3. Derivative of the bottom. 4x plus 1, right? Now, let x go to infinity. What do we get? Infinity minus 3. Infinity over infinity. Yeah, so we get infinity over infinity again, right? No worries. L'Hopital's rule works anytime you see infinity over infinity or 0 over 0. And if you see it again, then you do it again. Right? So now L'Hopital again. Second time L'Hopital comes through. Derivative of the top. 2, derivative of the bottom, 4, 2 divided by 4, 1/2. Done. Yeah, okay, so yeah, it says it in the book. L'Hopital's rule is named after French nobleman Marquis de L'Hopital, 1661 through 1704, but was discovered by Swiss mathematician John Bernoulli. Okay, y'all know Bernoulli? Y'all have heard of Bernoulli or no? John Bernoulli? No? No? You haven't? Okay. Well, he's very famous. So Bernoulli discovered it, but was being funded by this nobleman, okay? And so the nobleman gets his name on it. So I'm going to have to like unwire this thing in my head about L'Hopital. I'm just going to have to unwire it. Bernoulli, right? Bernoulli. This is awesome, right? So inevitably students will ask me, you know, why did we have to suffer so much, right? Like, why did we have to suffer through the limits so much? Why not just give this in the beginning, right? So why not?
Because you don't always have infinity over infinity or 0 over 0.
Yeah, but when we did, it would have been nice to have this, right? Wouldn't it have been nice? So, we didn't have the derivative. Okay, so that's the key. You can't put the carriage in front of the horse, right? When we were talking about limits in the beginning, we were just talking about limits. Then we use the limit to develop the idea of the derivative. The derivative is actually the limit as h goes to 0 of f of x plus h minus f of x all over h, right? So then we build from that, and we say, oh, there's these cool shortcut formulas, blah, 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 blah. And now we're saying, oh, wait a minute, you remember limits? We can actually use derivatives to solve limits. So it wasn't that we're holding it off on you. It's just that if I would have walked in and said, oh, just take derivative of top and bottom, you'd be like, what's a derivative, right? So we had to do it in this order. But now we have it. And from here on out in this class, anytime you have a limit, this is fair game. Now there are times where L'Hopital will fail us, all right? So let me just modify this problem slightly. So even though it looks like the cure-all for everything, for all your math ailments, it's not always going to be the case. So that problem right there, we can do that one. We can do that one algebraically, by hand. We get infinity over infinity. And what we would do, we did in class, it was like we would figure out what would make this thing a 1. So I would have to come out here with the 1 over x squared, 1 over x squared, and when the x squared goes in, it gets squared. Go back and watch a video or notes or something, but we can do this by hand. So this is achievable, but let's see if L'Hopital will get us there. L'Hopital, do y'all see the problem already? What's the problem? Derivative of the top's not bad, right? It's the derivative of the bottom that's bad. Because the derivative of this requires a chain rule, right? It's 1 over 2 root x to the 4th plus x squared plus 1 times the derivative of what's inside, which is 4x cubed plus, plus 2x, like that. And now this expression is just ugly. And if you try and let x go to infinity here, you're going to wind up getting infinity over infinity over infinity, and so you haven't gotten any better. So then you say, okay, maybe I can do L'Hopital a second time. Does anybody feel like taking the derivative of that? Probably not, right? Especially this, because this down here would be a quotient rule, and there's no way around it. But we could do this algebraically, right? All right. We have 10 minutes. I'm going to give you one more little thing, and we're going to come back and do more of this later. More limits next class. Let's take a look at this one. Well, you know what? Let's make that. Yeah, no, let's do that. Kind of regret doing this one now. Let's do it anyway.
No regrets.
Yeah. Well, let's just first see what's happening. As x goes to infinity, this becomes infinite, right? So we have something that looks like infinity times. Now here we have sine of fixed over infinity. Fixed over infinity goes to 0, right? So this goes to 0, and sine of 0 is approaching 0, right? So this goes to 0, this whole thing. Is that an indeterminate form? Something wants to be big times something wants to be small. That's indeterminate, right? Can you use L'Hopital's rule? No, why not? It's not 0 over 0 or infinity over infinity, right? It's got to be that format to do it. Some people think, oh, L'Hopital, I just do it for everything. And so I just take derivative of each one, and that's it, I'm done. No, you have to have this look like a quotient. So watch what I'm going to do. And you'll do this every single time you ever have this. You will look at your two factors, right? There's this one and this one. And you're going to make a choice. You're going to make a choice to rewrite this expression with one of those factors dropped to the bottom. Now let me do it first, so you'll see what I mean. I'm going to leave the sign of 1 over x up here. And then I'm going to create a fraction. And on the bottom, the x is going to be dropped down. But I can't drop it down and put x here, because that's not the same expression. So what I put is 1 over x. Do you all agree that that's the same problem? Right? 1 over x would just flip up and become the x up here. Now look at these individually. If I let x go to infinity, we already said this goes where? 0. And now look at where the bottom goes. 0. And now you have 0 over 0, don't you? And now you can apply L'Hopital's rule. So if I continue, you know what, I'm going to keep doing L'Hopital. I'm going to keep doing it, because you know what? He had the money at the time, and you know, it's the way things go. Bernoulli has plenty of other accomplishments, all right? Sometimes you got to buy your fame. Okay, derivative of the top. Careful, derivative of the top. Cosine of 1 over x times, okay, where'd that come from? Yeah, that's my power rule on 1 over x. So just rewriting 1 over x as x to the negative 1, and then taking its derivative. The negative 1 comes out, x to the negative 2, right? And if you rewrite that, you get this over there. I think the derivative of 1 over x comes up enough from here on out that you should try and memorize that one. If not, just see. If you're not just going to see it, then at least try and memorize it. Kind of like I asked you to memorize square root of x. Derivative is 1 over 2 root x. Just memorize the fact that derivative of 1 over x is negative 1 over x squared. So what is the bottom? Negative 1 over x squared. And let's cancel. And now, let x go to infinity. All you have is this left, right? So 1 over infinity, fixed over infinity goes to 0. Cosine of 0 is 1. So what happened here is that this guy right here was like, I want to be real big. I want to be real big. That's what I want to do. This guy's like, I want to be 0. And then they just kind of had a talk, you know. Maybe they had a mediator come in. And they decided, you know what, we're just going to compromise on 1, all right? So graphically, if I were to take that expression, x times sine of 1 over x, and graph it, what I should see is as we go to infinity, as we go out to the right, as we keep going out this way, the value of this function is approaching 1. It's kind of easier to see it here in the beginning, because in the beginning it was like, they weren't happy with life, and then they finally said, all right, we're going to work together and become 1. All right? All right, so all we've done right now is we've learned that if we have 0 over 0, infinity over infinity, L'Hopital's in play. 0 times infinity, we're going to take 1 and drop it, and then do L'Hopital. We still have to talk about 1 to the infinity, 0 to the 0, all that, right? We still need to talk about all those indeterminate forms, infinity minus infinity. And we'll cover all of that starting next week. Okay? And then we move to chapter 4. Yeah? Okay. So if you want to start your homework for 3.7, you should be able to handle some of it. Not all of it, but 3.7, where is it? Actually, you can probably handle 1 through 22. Any problems 1 through 22 you should be able to handle. They're all within striking distance for you. All right, quiz on Tuesday?
And then you said test 14th.
14th of November. Yep. Still a little ways off, but. All right, everyone. Have a great weekend. Oh, I have your quizzes. If you want your stuff back from last time, I have those. Sorry, I posted the grades before class. Those of you who gave me those folded up ones for the extra points, I added those. And then these are the other quizzes. I'll just put them on this table. Y'all can kind of sort through that.
What's going to